Hello, grade 10s. In today's lesson, we are going to learn about longitudinal pulses and waves. Now, we've just finished learning about transverse pulses and waves, and what we're going to find is that even though the shape of a longitudinal wave is different to that of a transverse wave, the same definitions and the same formulas still apply. So we're going to define a longitudinal pulse and wave. We'll differentiate between longitudinal and transverse waves. We will learn how to draw a diagram to represent a longitudinal wave. In a transverse wave, there are crests and troughs, but in a longitudinal wave, there are compressions and rarefactions. We will define those. We will also redefine the wavelength, amplitude, period, frequency, and speed of a longitudinal wave. We will use the relationship between frequency and period to solve problems in the same way that we did when we learnt about transverse waves. We will define wave speed and use the wave speed equation to solve problems, again, in the same way that we did for transverse waves. Now, the main example of a longitudinal wave is a sound wave. We will explain the relationship between the sound wave speed and the properties of the medium through which the sound wave travels, whether it is a solid, a liquid, or a gas. We're going to learn about echoes, about the flash and bang method, and about sonar technology, and we're going to apply calculations based on questions involving these using speed equals distance over time. We will relate the pitch of the sound to the frequency of the sound, the loudness of the sound to the amplitude of the sound, and the tone of the sound to the quality of the sound. We will look at the graph shapes produced by pure notes, music, and noise. We will describe the range of human hearing as well as ultrasound and infrasound. We will explain how an image can be obtained using ultrasound, and will describe medical and other uses of ultrasound. So let's start off by defining longitudinal pulses and waves. Recall that a pulse is a single disturbance that moves through a medium, whereas a wave is a regular and continuous disturbance that moves through a medium. Now, we learned about transverse pulses and transverse waves, where the particles of the medium move perpendicular to the direction of the propagation of the wave. So that means that the wave is traveling in the x direction, and the particles that make up the medium are disturbed up and down, making a 90-degree angle with the direction of the movement or the propagation of the wave. Now, that is different to the shape of longitudinal pulses and waves. And the main example of a longitudinal wave, and really the only one that we're going to deal with, is a sound wave. So anything that generates a sound creates a longitudinal wave. A longitudinal wave is considered a pressure wave because the particles move back and forth, and that results in compressions and rarefactions, which are areas of high pressure and low pressure within the medium in the direction of the disturbance. So here we can see a transverse wave and a longitudinal wave shape. In a transverse wave, the particles of the medium move up and down. So they move up and down relative to the direction in which the wave is moving. In a longitudinal wave, the particles move back and forth relative to the direction in which the wave is moving. And that back and forth movement creates areas of high pressure, known as compressions, and areas of low pressure, known as rarefactions. We're going to look at a longitudinal wave demonstration using a slinky. But of course, longitudinal waves are created by sound, not by slinky coils. However, this will give you an idea of the direction of the wave relative to the direction of the particles of the wave. So in slow motion, we can see that the wave is moving in this direction, but the vibrations are moving back and forth. So it's moving forth and then back, and forth and then back. When the particles move forward, they create areas of high pressure, meaning compressions. And they therefore, by definition, create behind them areas of low pressure, and that would be called the rarefaction. But once the sound wave has moved through the medium, the particles diffuse back into their normal position. If this is still confusing, I'm going to describe it again shortly. But first, let's complete some definitions. So what is a longitudinal pulse? It is defined as a single disturbance where the particles of the medium move parallel to the direction of the propagation of the pulse. So the definition is the same as the definition for a transverse pulse. The only difference is the word parallel that goes hand in hand with longitudinal pulses and waves, as opposed to perpendicular, which goes hand in hand with transverse pulses and waves. What is a longitudinal wave? It is a series of disturbances where the particles of the medium move parallel to the direction of the propagation of the wave. So again, same definition as before, but the difference is the key word here, which is related to the direction in which the particles of the medium are moving. Now, a compression is specific to a longitudinal wave, as is a rarefaction, and a compression is defined as a region in a longitudinal wave where the particles are closest to each other or at high pressure, whereas a rarefaction is a region in a longitudinal wave where the particles are furthest apart from each other or at low pressure. So here's another diagram which represents a longitudinal wave. In this case, the propagation of the wave, meaning the direction in which the wave is moving, is to the right. And when a sound is generated over here, it pushes forward the air particles in front of the object that's generating the sound, and that creates a compression region. Now behind it would be a region of rarefaction, low pressure, because the particles have been displaced forward. Now, these particles over here are going to push forward on the particles next to them, which creates a low pressure region behind those particles. So it's just like a domino effect, but where the dominoes move forward and compress, the areas behind them rarefact, meaning that they create a low pressure region with fewer particles. But after the particles have compressed and rarefacted, they move back to their original position due to the natural process known as diffusion, where particles of fluids, meaning particles of liquids and gases, move around randomly until they reach an equilibrium, meaning that they become equally spread out. So the air particles become equally spread out again soon after the sound wave has passed through them. So imagine a domino scenario and imagine that the dominoes naturally move back into their original position. Now, when it comes to wavelength, amplitude, period, frequency, and speed of a longitudinal wave, they mean the exact same thing as when we learnt it for transverse waves. Now, diagrammatically, we represent a longitudinal wave like this. If you're asked to draw a longitudinal wave, you simply draw areas of low pressure followed by areas of high pressure using straight vertical lines. They don't have to be perfect, they don't have to be measured, they don't have to be drawn with a ruler, but the general shape has to be apparent. Recall that when we learned about transverse waves, we defined the wavelength of a transverse wave as the distance between any two successive points that are in phase, and this definition still applies. The only part of the definition that changes is the example part. So for a transverse wave, we said it's the distance from crest to crest or from trough to trough. But longitudinal waves don't have crests and troughs. They have compressions and rarefactions. So it would be, for example, compression to compression distance or rarefaction to rarefaction distance. So again, in the case of a longitudinal wave, this may be the distance from the center of one compression to the center of the next compression, or the distance from the center of one rarefaction to the center of the next rarefaction. Now, this can be quite confusing when a longitudinal wave is represented graphically. This is not often the case on tests and exams, but sometimes a longitudinal wave is represented graphically, meaning that it has the same shape graphically as a transverse wave, but this is not to be confused with a transverse wave. My advice is that when you're faced with a waves graph, read the question very carefully. If it is a water wave, it is a transverse wave. And if it is a sound wave, it is a longitudinal wave. Now again, this is confusing because a longitudinal wave in graph form takes on the shape of a transverse wave. However, in this form, it is easier to identify the wavelength and the amplitude, the period and the frequency of a wave. Recall that the amplitude of a wave is the distance of the maximum disturbance of the medium from the equilibrium position. So that would really be the distance that those particles are pushed forward, creating the compression. But if this sound wave is represented on a graph, then it becomes easy to read off that amplitude. If we represent a longitudinal wave on a graph, then the amplitude is the distance from this equilibrium position to where the particles are at maximum pressure. Maximum pressure of the particles is the center of a compression, and the center of a compression is represented by the crest of the wave. We can see that here too. The center of a compression would be represented by the crest. The amplitude is also the distance from the equilibrium position to where the particles are at minimum pressure. That would be at the center of a rarefaction. The center of the rarefaction is represented by the trough of the graph. The period of the wave has the same definition as previous. However, the example over here is a little bit different because we're dealing with a longitudinal wave that has compressions and rarefactions rather than crests and troughs. So the period of a wave is the time that it takes for one cycle to pass a fixed point. But in this case, one cycle would be two successive compressions or two successive rarefactions. The frequency of the wave, also the definition remains the same. It is the number of cycles that pass a given point in 1 second. But again, in this case, a cycle is two successive compressions or successive rarefactions, not successive crests or successive troughs. The frequency and period of the wave are still inversely proportional. Therefore, we may still use these two formulas. Frequency is 1 divided by period, and period is 1 divided by frequency. And the speed of the wave is defined as the distance traveled per unit time. And it has the same formula. The wave speed is the wavelength divided by the period, or the wave speed is the wavelength times the frequency. So let's take a look at some examples. Number 1. A longitudinal wave has a compression to compression distance of 10 meters, and it takes the cycle 5 seconds to pass a fixed point. So the first thing you need to do is understand what variables are given to you here. Compression to compression distance of 10 meters means the wavelength. So the wavelength of this wave is 10 meters. The fact that it takes the cycle 5 seconds to pass a fixed point, that's the definition of the period of a wave. How long does it take for a full cycle to pass a fixed point? And in this case, the period of the wave is 5 seconds. So we have the wavelength and the period of the wave. The first question is, what is the speed of the wave? We may calculate the speed of the wave as the wavelength divided by the period, which is 10 divided by 5, and the answer is 2 meters per second, because speed is measured in meters per second. What is the frequency of the wave? Well, given the period of the wave, we may work out the frequency as 1 over period, which is 1 over 5, which is 0.2 hertz. And what that means is that 0.2 wave cycles pass a given point in a second. A mosquito beats its wings at an average rate of 600 wing beats per second. The speed of the sound wave is 340 meters per second. So we have the speed of the wave, and this is what the mosquito is generating with its wings. 600 wing beats per second. So from that, we need to understand that this represents the number of hertz. It's the frequency. Because remember that frequency is cycles per second. The thing that is generating the sound is the movement of the wings, which are moving at a frequency of 600 beats per second. So the first question is to calculate the wavelength of the sound wave made by the mosquito by its wings. And like I said, we need to understand that we need to understand that this 600 actually represents a frequency of 600 hertz. So we're looking for a formula that includes the speed, the wavelength, and the frequency of a wave. In this case, we were asked to work out the wavelength. So I've rearranged my formula as wavelength is equal to speed divided by frequency, which is 340 divided by 600. So the wavelength would be 0.57 meters. What would be the wavelength of the sound wave if the mosquito halved its wing speed? Now, that's a little bit confusing, because by saying that the mosquito halved its wing speed, what are we actually halving? We're not halving the speed of the wave. And remember that the speed of the wave depends only on one thing, and that is the medium through which it travels. And that hasn't changed. Halving the wing speed means that we're halving the frequency. So it started off at 600 beats per minute, and now it is 300 beats per minute. So by halving the frequency from 600 hertz to 300 hertz, what would happen to the wavelength? For that, we need to recall the relationship between wavelength and frequency. If I halve this frequency value over here, what will happen to this wavelength value over here? What will double? Remember that frequency and wavelength are inversely proportional, provided that the speed is constant, and we know that the speed is constant. So the answer is that half the wing speed means half the frequency. If the wing speed is halved, meaning that the frequency is halved, then the wavelength will be doubled. The wavelength, the original wavelength, was 0.57 meters. So 0.57 times 2 is equal to 1.14 meters. And this is because frequency and wavelength are inversely proportional. It's very important to include this statement over here. An elephant trumpets and creates a longitudinal wave. The speed of the sound wave is 344 meters per second. The wavelength of the wave is 37 meters. Calculate the period of the wave. So we've been given the speed of the sound wave and the wavelength of the sound wave, and we want to figure out the period of the sound wave. So we have to look for a formula that includes speed, wavelength, and period. And that would be this formula over here. Wave speed is the wavelength divided by the period. Now we're asked to work out the period, so rearranging the formula, the period of the wave is the wavelength divided by the speed, which is 37 divided by 344, which is 0.11 seconds. So that is the amount of time that it takes for a full wave cycle to pass a given point. In the next lesson, we will continue on sound waves.